Hey folks, normal distribution, the bell curve. I'm going to show you how to do everything the long way using a z-table, and then I'm going to show you the shortcuts on the calculator. That way, once again, you can appreciate the magic and power of your calculator. Also, I keep referring to it as 7.2. That's from a different book, so just ignore every time I say 7.2. Okay, normal distribution.
Hey folks, remember earlier we did this worksheet when we were doing the binomial and we figured out when we had Shaq playing basketball, right? So I just rewrote it right here for a second. So we had Shaq and he attempted 2 shots and he has 20% at the line, and we got those probabilities right here. So I'll try and insert a picture into the video, but I'm going to pretend you can see this. Turns out, does this work? Not very well. There's a whole table of binomials. So you can see that 0.64, 0.32, 0.04. And you can't see it at all. I'll insert a picture. So anyhow, there's a whole table of probabilities. So if the probabilities are nice, like 0.2, 0.3, 0.4, then there's a table full of probabilities. So I was looking at a table of probabilities and I got these numbers, so rather than do the math, just go along with it. But if I were to graph a picture, these all add up to 1, right? Obviously. And if I were to graph a picture of it, it would look something like this, right? This level here's at about 0.1250, and that's 3 times as high, 0.3750. So this is for n equals 3. This is when I'm doing 50-50. You see how it's nice and symmetric? See how the numbers are symmetric? That happens when it's 50-50. So here's the picture when n is 3 and p is 50-50. So here's a picture. Let's say it was like n equals 7. Making this up. P of 0.50. It's going to look something like this. It's going to be nice and symmetric is the main point. So let's say, we keep running with that idea. So let's say it's like n equals 20 and p equals 0.5, and we were to graph it. The picture would look very similar. It'd be symmetric. And it looks something like that. And if you were to add up all of those probabilities, they would have to add up to 1. So let's say we keep taking this 50-50 idea all the way out forever. It ends up forming a nice, weird bell shape. So the bell curve, or the normal distribution, if we were to shade the whole thing in, by definition, it's analogous to this. It must have an area equal to 1. Very good. Let's say I were to shade in the left side of the bell curve. The area must be equal to 0.5. Notice it's symmetric, so the bell curve is symmetric. Total area under the curve is 1. If I were to shade the right side, 0.5. Okay, so we know where the bell curve comes from, and the area, total area, it's symmetric. Total area under the curve is 1. I shade half of it, 0.5. Okay, let's draw the picture a little bit better. The bell curve is resting on top of a number line. So let me draw the bell curve first. Okay, so in the very center, let's just put a 0. And then if you want the picture to look really nice, so imagine, if you will, there's a snowboarder up here, or a skateboarder or something. And as they're going down the hill, it's getting steeper, 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 till about right there. So the hill is getting steeper, 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 and then it starts to mellow, 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 mellow. So if you've taken calculus, that's called an inflection point. So notice the other way, it's getting steeper, 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 till about right there, and then mellow, 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 mellow. So that distance, we'll say, so is a distance of, we'll call it a standard deviation 1. And so this would be, because it's a number line, this would be -1. So once I have that sort of distance established, if I repeat that same distance, -2, +2, 3, -3. So 0 in the center. This is our standard normal curve. We'll talk about other normal curves, but in the standard normal, the distance of the standard deviation is 1 and the center is 0. And it goes on forever. It's getting really, really thin, though, at the edges. I didn't draw it very well. Okay, and if I were to shade all of it, the total area would be 1. Excellent. So here's the question. What if we have a bell curve, center is 0, so I usually put a tick mark with a 0, and what if at, let's see, what if at -1, so I'm looking at the worksheet now, -1, so here's -1, what if I shade everything to the left? So what's the probability? So once we have this picture, we're going to call it Z, that Z is less than -1, and that's what you should see on your little worksheet. The probability that Z is less than -1 is just this picture. So I don't know what the answer is yet, but I know it has to be less than 1. I know it has to be less than 0.5, right? Because if I were to shade half the bell curve, that would be 0.5, and this is less than it. So my answer better be less than 0.5. Okay, so I'm going to post a picture right now, and you'll see that next to the -1 is the area of, let's see, I actually have this here, but I'm going to post it in your little, in the video. So right next to -1, I see 1587. So this area is 0.1587. So this is 0.1587. I'm going to show you how to do this on the calculator, but right now I like showing you old school way. Okay, so going to the worksheet, the next one says probability that Z is less than -1.73. I'm going to post a picture. 0's in the center. -1.73 is somewhere over here. Which way do I shade? To the left. Left tail, which it has two tails, right? Which tail gets shaded? This one's pointing that way. To the left. Okay. So my little table that I'm going to post for you in the video is left tail. And so I go down to -1.7, and then in the column of 03, and I should see 0418. 0.0418. -1.73, 0418. So that's my answer, 0.0418. How much area is to the left of -1.73? About 0.0418. Okay. So then, is this making any sense? I hope so. You can always pause and rewind, right? Question 3, probability that Z is less than 1.58. Again, post a picture, but using my little table, I would go to 1.5, column 8. First I draw a picture. 0 is in the center. 1.58 is somewhere over here on the right side. Which way do I shade? See how it's pointing to the left? It's a left tail. I have a left tail table. So I look up 1.58, go to 1.5, go to the 08. I see 9429, 0.9429. So that's my answer, 0.9429. Okay, question 4. Ooh, right tail. Probability that Z is greater than -1. Let's draw a picture. 0 is in the center. -1 is right here. Which way do I shade? To the right. See how it's pointing to the right? Right tail. But I have a left tail table. So here's what I would do. It's all about that 1 minus trick that you folks didn't like when we did a binomial. So if see how there's a left tail here? So why don't I just go 1 minus the area in the left tail? And then we say the area in that left tail was 0.1587 on problem number 1. So 1 minus this area. So look up -1, you get 0.1587. So subtract that and you get 0.8413. So that's how you deal with right tails. That's one way. There's a quicker way. Well, we're going to learn a quicker way with the calculator. But another way is you go, oh, if it's right tail, I could just look up opposite. It says -1. What if I just look up +1? Look up +1, aha, 0.8413. All roads lead to Rome eventually. So number 5 says probability that z is less than 1. Oh, less than? Less than's easy, just look it up. So if you just look up 1.8413. Oh, that's what we did a second ago when we looked up opposite. Aha. Okay. So probability that z less than 1. There's 1 because 0 is in the center. So you see how these two pictures look very similar. Imagine if you got a spatula and flipped it over. That's why their areas are the same. They look identical if you flip this guy over. Okay. This is a long worksheet. Okay, problem number 6. I'm going to show you how to do it on the calculator in a second. Ooh, fancy yellow paper. How long are we into this video? 10 minutes. Good gosh. Okay, problem number 6. Probability that z is greater than -1.73. Here's how I would do it if I was using a table. Is it left tail or right tail? It's right tail. Oh, if right tail, look up opposite. So I would just go to positive. So draw your picture first. -1.73, shaded to the right. Okay, is it left tail or right tail? It's right tail. Okay, if right tail, look up opposite. Well, it says -1.73, so the opposite is +1.73. So I look up +1.73, and I get 0.9582. Boom. Again, we're going to do this on the calculator in a minute, and you'll be like, why did I bother teaching you it this way? Because everyone needs to see a z-table and how it works. Okay, we'll get through. Okay, let's finish off 7 through 12, and then I'll take a break. You'll take a break. We'll all take a break. 7, scientific notation. Your calculator uses scientific notation, so I just want to make sure you're cool with it. 3.4 times 10 to the 4th means move the decimal 4 places in the positive. So you take that 3.4 and you move that decimal 1, 2. Some people do it like this. 1, 2, 3, 4. So the new number becomes 34000. See how we move that decimal 4 places to the right? Aha! 8. 1.28 times 10 to the -5. So what you do is you take the 1.28 and you grab that decimal and you move it 5 places to the negative left. 1, 2, 3, 4, 5. 0, 0, 0, 0. And so we get 0.0000, 4 of them, 1, 2, 8. Aha! 9. 5.11 times 10 to the -2. Move that decimal 2 places to the left. 0.0511. I just guessed. Double check. 2 places to the right. Yep, that looks good. So this time 10 to the -2 or times 10 to the -5, that's how we write it in science class, but our calculator can't really do these superscripts very well. So they would say something like 6.78 e minus 3, which is just their way of saying 6.78 times 10 to the -3rd, which is just 0.00678. Okay, it's making sense. 11 is 9.213 e -5, which is just their way of saying 9.213 times 10 to the -5th, which is just 0.1234 9213. Oh my, can we even see that? Okay. And then, is there a number 12? Of course there's a number 12 that I need to waste another piece of paper for. Okay, number 12. Wasting paper. 4.92 E4 is just 4.92 times 10 to the fourth, which is just 49200. Move it over, 1, 2, 3, 4. Dun. So you're going to see on your calculator, let's say we want to write this number on our calculator, 4.92 E4. You would do it like this. Let me make sure we can see this. You would say 4.92, and instead of E, they call it EE to be annoying. 4.92 EE, but it says EE, but then it only prints an E. Confusing. 4. Enter. Ta-da! Okay, calculator makes sense. We'll pause there. Whew.